So let us start this last session of this wonderful conference. And before we start the last session, I would like to have a big round of applause for all the organizers for putting up such a good effort. So we have a bit tight schedule, so we may have just 1 or 2 questions, not many in this session. And start this session now with the local boy, Tomasz Downarowicz, who's going to speak on asymptotic pairs in actions of amenable groups.
Thank you very much. And traditionally, I will start by thanking the organizers for the invitation. And without any further ado, let's get to the point. I promised that in my lecture, the word nil will appear. So it is now and only now. Amenable groups include nilpotent groups. So everything I say applies to countable nilpotent groups as well. Thank you. Okay, so as you can see from the title, the subject are asymptotic pairs and their appearance versus entropy of an action of an amenable group. This is okay. This is based on a joint work with my student Mateusz Więcek from Wrocław Technical University, and let's start. The motivation is a classical result or two classical results, which are as follows. If a topological system has positive topological entropy, then we are sure to find in this system an asymptotic pair. Moreover, the set of all pairs, or if you unite all the pairs as a one set, then you have something of positive measure. And this is due to Blanchard-Host-Rouet classical result from 2002. Then another result in the opposite direction, which is due to myself and Yves Lacroix 10 years later. So as you can see, it needed to wait a little while to get the opposite direction, because it is not true that a system with zero entropy does not have asymptotic pairs. We all know that any expansive system has forward asymptotic pairs, but you can extend the system to something which does not have asymptotic pairs, and we call such systems nap. Like maybe one of you will take a nap, so this is more or less the same. No asymptotic pairs. And of course, this extension, because of the first part, must also have entropy 0. Okay, so we can characterize zero entropy systems as precisely factors of the NAP systems, which is nice because calculating entropy is more complicated than just checking for asymptotic pairs, which are visible by naked eye usually. Okay, so because everything that is known for classical systems is being generalized to countable amenable group actions, I thought it might be a good subject for a PhD student to work on. And I asked this following question: is there a reasonable definition of an asymptotic pair in an action of a countable amenable group so that an analogous characterization of zero entropy holds? And of course, if you think about a definition of an asymptotic pair in some completely abstract countable group, then one thing that comes to your mind is, okay, let the pair be close, follow the same trajectories almost, except for a finite set. So for each epsilon, only finitely many elements of these two orbits are apart. Otherwise, they're close. So they approach each other as we go away from any finite set. But this definition is not good even for Z actions, because for Z actions, that means that the pair is asymptotic both forward and back. And there are known examples of systems with positive entropy which do not have such pairs. Actually, there is a whole story of bilaterally deterministic systems. So I'm not going into details, but this definition is out of question for trivial reasons. So it seems that we need to look at some kind of future. The forward asymptoticity is what we really need. So if a group is orderable, that means has an invariant order, then there have been successful attempts and of at least one direction, the direction of existence of asymptotic pairs in positive entropy. That was done by Huang, Xu, and Yi, and independently by the team from Toruń, Bułatek, Kamiński, and Szymański. So, okay, but yes, but yeah, for Z, but we want to work in general. If you take homoclinic point, yes, I guess. But as I say, this is not what we are looking at, because this bilaterally asymptotic pairs is too strong. Okay, so the first question is, how can one define future of an orbit? And we do it by introducing a complicated machinery, and I'm going to explain this machinery for a while. So there is a notion of something that replaces an invariant order in a non-orderable group, and this is called an invariant random order. That is a family of orders, total orders, on which the group acts as follows. This is I call it pretz, because in LaTeX you put \pretz. So I call it pretz. So this pretz is an element of this family of orders. And then this G of pretz is another order, which is defined by this relation. So A is G of pretz less than B if GA is less than GB. So we have a natural action of the group on the family of orders. We want this family to be invariant, and we want an invariant measure. And we want an invariant measure. Sorry, this is too much. We want an invariant measure on this family of orders. So this is what we call a multi-order or invariant random order. But our invention was slightly more restricted. We want all these orders to be of type Z. An order of type Z is defined by either order isomorphic to Z, or by all order intervals are finite and there is no maximal nor minimal element. Okay, so these more general I rows were defined by Kiefer in '75, and he showed that any countable group can have a multi-order like this. However, most of them are of type Q. That means between any two, each order interval is countable. We wanted something that is finite, and this is the team who introduced this notion, and we proved that such objects exist on any countable amenable group. So, and Downarowicz helped us to show that any multi-order has the Fellner property, which is very, very nice and very useful. Here is what it means. For almost any pretz in this multi-order, the order intervals, this is my notation for the zero element. So 0 is always 0, is the unit of the group. I start counting from 0, and then n pretz is the nth follower or nth successor of the unit in our order pretz. And this is everything in between, inclusive. So these intervals form a Fellner sequence. And I'm not going to explain Fellner sequence in this community. In any case, this resembles very much the standard situation in Z. In Z, you take the order intervals from 1 to n or from 0 to n, and these form a Fellner sequence. So we have a very, very similar situation, except that you don't have one order, you have many orders. So this one order is a family which is invariant because this order is invariant, and the point mass is a Fellner multi-order on Z. So this is a direct generalization to other groups. So these properties which I just mentioned are crucial in proving the classical theorems. So we think that this multi-order is a good starting point. Okay, so now we need a dynamical system or a G action. And actually, this is the measure theoretic part. I forgot to mention that Blanchard-Host-Rouet result is more measure theoretic, and the other result about the extension is more topological. So here is the measure theoretic part. We start by defining multi-ordered measure preserving transformation, which means that there is a factor by some transformation phi from our space to a multi-order. So a system is multi-ordered if it has a multi-order as a measure theoretic factor. This is very convenient because then every orbit, every point is associated to every point you associate some order of type Z. That means your orbit can be ordered like Z. And to those who are familiar with orbit equivalence, this should ring a bell. This is nearly the same as the fact that any amenable group action measure theoretically is orbit equivalent to a Z action. So this is parallel result. One can be derived from another. Okay, so for Z actions, every Z action is multi-order because this one order is a trivial factor of everything. Okay, so in a multi-ordered system, we know what the future of each orbit is. It's just the, you must get to use this, you should get used to this notation. N Pretz, it's the n follower of 0 in our order Pretz. So you take the future of the orbit is simply the images of X via the elements that are in the future of our order. Or if you start from some capital N, then we call it the remote future. So we can define now asymptotic pairs in a multi-ordered system. A pair XY is asymptotic if three conditions are satisfied. First of all, they must be distinct because for the same point is trivial. They have to correspond to the same order. So they must project to the same order. Otherwise, you cannot compare them. And you want the usual asymptoticity condition that their future images approach each other as time passes. Okay, so for Z actions, we have this one order, classical order as image of everything. So all pairs satisfy the second condition. And this is just the standard notion of asymptoticity. So again, this is direct generalization of the classical notion. And we will also need, for the other direction, we will need something like topological multi-ordered systems. This is more tricky. Why? Because if you take a multi-order and you close it, you think of a multi-order as a set of bijections from G to Z or from Z to G. Bijections can go either way. So if you take closure of a typical multi-order, it's gonna contain some objects which are not orders of type Z. There will be orders of type N or of type -N, or maybe even partial orders. So there is little hope to get something like a closed compact system, which is a multi-order. This is why instead we introduce a topological multi-order as something that passes through another object, which is a system of tilings, tiling system. And unfortunately, I need to familiarize you with this other notion of a tiling system. So what is a tiling, first of all? We have our group and we partition it into finite sets. And we require that all these sets are shifts of some finite family of sets, which we call shapes. So maybe everybody is familiar with this picture. Here we have how many shapes? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Maybe a little more, I am not sure. But there is a finite family of shapes and everything here is covered. This is Penrose tiling, of course. So if you have a tiling, you can shift it. Well, like in this picture, you can imagine that you shift the whole thing by some element of Z2. Well, we imagine this to be a tiling of Z2. Of course, you have to imagine a lattice of points inside. So we can shift any tiling and you get another tiling with the same family of shapes. And moreover, if you take orbit closure of a tiling and it shifts, you get, again, good tilings. So there are no strange elements. Unlike for the multi-order, if you take a closure, you get partial orders or orders that are not of type Z. Here, there is no danger. If you take tilings, start shifting, take the closure, you still get tilings. So a tiling, dynamical tiling is a G action by shifts on a closed invariant family of tilings with a common family of shapes. And the typical dynamical tiling is just orbit closure of one fixed tiling. So we have these objects. And then the next object is a tiling system. It's a joining of a sequence of tilings with larger and larger shapes. And there are several requirements here. The first one is the Fellner property. That means that if you take all shapes in all those tilings and arrange them in a sequence, you get a Fellner sequence. This is called a Fellner property of the tiling system. Then there are two more. The element of this joining is a sequence of tilings belonging to these dynamical tilings. So we have this tau, boldface tau is a sequence of taus, calligraphic taus. And what we require is congruency. That means that every tile of tau k plus 1 is a union of the tiles of tau k. And moreover, we want these to be uniquely determined by the shape of the larger tile. So if you see the shape of a larger tile, you know exactly how it's subdivided. Okay, so I made this summary of notation because there are so many T's that it may be confusing after a while. So tau is a static tiling, that means not moving. T is a tile. This straight T is a dynamical tiling, which is a family of static tilings invariant under the shift. And this boldface straight T is a joining of such things, which we call a tiling system. And an element of this tiling system is this boldface tau, which is a sequence of taus, tau k. So sorry, there are so many taus, and I myself getting lost in this notation. So I practically did this for myself as well. Okay, so here is a theorem which I proved with David Huczek and Guohua Chang some years ago. Every countable amenable group admits a tiling system of topological entropy 0, which is very convenient in many aspects. So here is a picture that shows one element, part of one element of this sequence, tau k. So the first one is the blue tiling. Then I marked several shapes or tiles of the next generation. And maybe the whole thing, which is framed in black line, is a tile of the third generation tiling. And you can also imagine that this whole thing is moving by shift. So this is what a tiling system is. Okay, so now there is a link between tiling systems and multi-orders. Namely, you need a tiling system to be ordered. What does it mean? Well, you take the shapes of the first level tilings and order each shape, its element from 1 to the number of elements. I am not going to, I don't have figures for that, but you can imagine that you just enumerate the elements in each shape. And then as you look at the tile, you shift this enumeration to this tile. So each tile is enumerated from 1 to some number. And then because of the congruency and determinism, each shape of the next generation tiling splits in a unique way as a union of tiles of order k. So we demand that the subtiles are also ordered linearly from 1 to the number of subtiles. And by lexicographical order, we can, these orders, these partial orders on the tiles, they produce an order on each tile of any generation. All its elements are lexicographically ordered from 1 to the cardinality of the tile. And we are interested in these elements of the tiling system, which determine a total order on the whole group. And we want this order to be of type Z. This is like in multi-order. So here is the definition. An element of the tiling system is straight if the union of the central tiles, the tiles containing the unit, covers G. So we want the tiles to grow in all the directions, I can say it like this. And then the orders on the central tiles converge to a total order of G, of type Z. And we denote this order by Pretz sub tau. So what we have proved in yet another team, which is a combination of the two teams that I mentioned before with Chang and Oprocha and my student Więcek. We proved that if T is an ordered tiling system, then the collection of the straight elements which generate an order of type Z is large in both topological sense and in measure theoretic sense. So this is really a huge subset. And we look at the collection of all orders, Pretz sub tau, as tau belongs to this family of straight elements, and we call it topological multi-order. Why topological? Because it arises from the topological system, which is the tiling system. The tiling system is a genuine topological system, and this is almost everything in there. Okay, so we have the mapping from tau to Pretz tau. It's defined and continuous, which is easy to check on this subset, commutes with the action of G, and the action of G on the tilings is the shift, and on the order is the action defined earlier, like so. So we have a factor. We have a factor, but not defined everywhere, defined on a large set. But this set has full measures. So for each invariant measure, this mapping is a measure theoretic factor map from this set with the measure mu. This set supports the measure mu, so we can forget about topological thing, to the multi-order, which is defined as this, where nu is the image of mu. So a topological multi-order is at the same time, a family of multi-orders for every invariant measure on the tiling system. Okay. So now we have a theorem which is a very strong Fellner property. These topological multi-orders have a very strong topological property, which is as follows. Not only the usual Fellner property was that for almost every Pretz, the initial intervals form a Fellner sequence. Here we know that there is for each epsilon and k, because the Fellner property is defined as k epsilon invariance, right? I'm not going to remind you what that means, but for each epsilon and k, there exists some n such that for any element of this topological multi-order, any order interval of length at least n is k epsilon invariant. So it's a very strong uniform Fellner property, which is very crucial for what we want. And the same is true for Z. If you take any interval of length n or larger, it is n epsilon invariant, regardless of where you take. Okay, so now we have the notion of a topologically multi-ordered system where we demand that there exists an ordered tiling system, which is a factor of our system. So we want our system to factor to a tiling system. And then this tiling system produces a topological multi-order. And we also require that the pre-image of the straight elements is dense for some technical reasons. We don't want some strange factors to be sticking out, sort of. Okay. So we have this mapping here now. We take for each x, phi of x is an element of the tiling system. This element of the tiling system is some tau, not phi of x, sorry, pi of x. This tau. And then this tau determines an order, which is Pretz sub tau. So to each x, we associate this Pretz sub tau. But this x has to belong to this family x stir, so that it has an image in T stir. So we have this mapping, we call it phi. And it's a mapping from our system directly to the multi-order. So it is defined and continues on a residual set of full invariant measure of x. I didn't say it, but it's a subset of x. And for any invariant measure, again, we have this thing that x mu g phi is a multi-ordered system in the measure preserving sense that I defined earlier. So again, the topologically multi-ordered system is measure theoretically multi-ordered for every invariant measure. We denote such a thing by x, g, pi, phi, because we need to indicate that our mapping phi is a composition of two factor maps. One is topological, one is almost topological. Okay, so well, I am in the position to present the main results now. I introduce all the terminology that's necessary to understand the main results. So the first direction is measure theoretic. We don't need the topological multi-order. We take any measure theoretically multi-ordered measure preserving action of a countable amenable group. And we suppose that the relative entropy with respect to the multi-order factor is positive. Well, if your multi-order to which our system factors has entropy 0, then this is just the entropy of our system. Otherwise, it's a relative entropy. It's not enough that the system has positive entropy. If your multi-order also has the same entropy, then there is no such thing. But if this happens, then there exists a phi asymptotic pair in X. That means a pair of points which factor to the same order, and along this order, they behave like an asymptotic pair. Moreover, the union of such pairs has positive measure. Maybe it even has measure 1. We haven't tried. There must be some ergodicity argument, I presume. But so far, we only know that it is positive measure. And then you can deduce that if you have an arbitrary topological G action on a compact metric space, and you take any multi-order, any that exists on the group, unrelated to our system, then there exists a Pretz asymptotic pair for almost any order Pretz in this multi-order. There exists an asymptotic pair. That means such that they converge to each other as n increases, as we proceed along this order, this common for the 2 points order. And the passage from 1 to 2 is very easy to see how to do it. You take a measure of positive entropy, and you look at the direct product of the measure preserving system on X and with the multi-order. And then this system is multi-ordered by projection on the second coordinate. So we let phi be the projection, and then the entropy, the conditional entropy, because this is a direct product, is the same as the entropy of the first coordinate, which we assume is positive. in this theorem. I forgot to say it here. Topological G action on a compact metric space. I forgot to write the main assumption that it has positive entropy. Only then we know that one applies because the conditional is positive. And for almost all Pretz, how do you get almost all Pretz? You get it by decomposing into ergodic parts, and on each ergodic part, the set of those Pretzes for which an asymptotic pair exists is invariant and has positive measure. So it must have measure 1 for each ergodic measure, and thus for any measure. Now, the opposite direction is not easy. So, of course, both statements are true, but you cannot directly deduce 1 from 2. Why? Because in 2, you know that for almost every Pretz, you have a Pretz asymptotic pair. But if you have a mapping from your system if you have a mapping phi of your system to here, for this to happen, you need a pair on the graph of phi. And the graph of phi may have 0 measures, so you cannot deduce directly. So the statement 1 is stronger, actually. But the statement 2 is nicer because it's more general. You take any system of positive entropy, which I forgot to write. Okay. The other main theorem is, as you can guess, the existence of a NAP extension for a 0 entropy system. And here we will use the topological thing. So the theorem is as follows. We have a topological action of countable amenable group of entropy 0, topological entropy 0. I made a mistake here. This should be topological entropy. Then there exists a topologically multi-ordered extension, YG pi phi of XG, which has no phi asymptotic pairs at all. Not only that the set of those pairs is measure 0 whatsoever, there are no such pairs at all. So as a corollary, we get that if we have a topological action, the following conditions are equivalent. The topological entropy, now I wrote correctly, topological is positive. Sorry? Yes. Oh, I was so excited that I have the correct subscript that maybe I made the following statement wrong. Okay, sorry. The topological entropy is 0 for any invariant measure which has positive entropy. This is nonsense. For any, no, this is nonsense. Sorry, forget about it. Cross it out. For any invariant measure mu on X, every measure has 0 entropy in this case. So there exists a multi-ordered extension which has no phi asymptotic pairs. Actually, it suffices that the union of asymptotic pairs has measure 0, but truth is that in that case, there are no asymptotic pairs. And the third one, there exists a topologically multi-ordered topological extension which has no phi asymptotic pairs. Phi is the factor from our topologically multi-ordered extension to a multi-order. So actually 1 and 3 is completely analogous to what happens in Z action. This is direct generalization. If you think of any Z action as being topologically multi-ordered by the one element factor. Okay, so this is the story. I have still 5 minutes. So I prepared some presentation, short one, how we built such an extension, because this was the most technical and most demanding part of these proofs. Okay, so let me introduce you to 2 more types of topological multi-order. So we have an ordered tiling system. So we know that each tile has an order and blah, 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 all this story. And we take such a thing of entropy 0. We know that it exists by some theorems on tilings that we proved earlier. Now, for each tau, And each tile, we move the center. So now maybe I will start drawing some pictures. So we have a tiling system. So we have those tiles here. And in each tile, we have an order. So maybe 1, 2, 3, 4, 5, 6, 7, 8. And the center is somewhere. It's the center of the tile. It's the place to which we shift the shape to obtain the tile. So we just decide that the center will be at the first place. And in this manner, we actually create a factor of our initial tiling, because for each tile, you know how to move the center. So you create a new shape now, because the original shape was centered here, and the new shape is centered here. So it's actually shifted like so. Okay, so we create new shapes, but there is still finitely many of them. So this is all correct. So we call this new tiling, which is the factor of the original, center, because each center is at the first place. Then we do another trick, which is more complicated. We want all the centers to be congruent in the order modulo some pk. We first fix some sequence of pk's, like in the odometer. Each pk must divide pk plus 1. And if I want to do here, I will put 1, 2, 3, 4, 5, 6, 7. And my center is here after centering the tiling. And now I decide that I want these centers to be congruent modulo maybe 5. So I choose here any number from 1 to 5 or to 4, maybe 4. And then I go 1, 2, 3, 4, 5. So it seems like I don't have to move. So maybe I move somewhere else. Maybe I move here. So I go 1, 2, 3, 4, 5. So in the next, this is my first tile of the larger tiling. This is my second tile of the larger tile. So because the next guy is here, modulo 5, I have to skip it because I cannot have two centers in one tile. And then I start counting 1, 2, 3, 4, 5. And then 1, 2, 3, 4, 5. So I move the centers like so, but I can do it in many ways because I can start from any place, modulo 5. So I can build many tilings of this kind above each centered tiling. And in this manner, I create an extension. So there's an inductive procedure. You do it on larger tiles, and then you make the larger tiles and so on. And in this manner, we obtain many tilings above each. So we get an extension of the centered tiling system, and we call it odometric tiling. And now if you unwrap this order, which will look like Z, what will happen? The centers will be congruent modulo 5. So if it's here, 1, 2, 3, 4, 5, maybe I skip this one, but then 1, 2, 3, 4, 5, I have another center. But the end of my tile is somewhere else. So my tiles are intervals, but the centers are congruent modulo 5 or modulo some pk. And in this manner, I have a structure which resembles that of an odometer. So this allows us, this is called ordered tiling, odometric tiling system. So then I take my general system, I take the direct product with an odometric tiling system, and we can encode it symbolically by some arrays, blah, blah, blah. But the main thing is that I can divide each orbit into equal pieces of length 5. And I will have the centers as sum of the division points. Now, this thing, this tile, this is not a tiling, unfortunately. This is why we have to do so much talking, because here between this and this, I do not control the jump. So this thing here, this order interval, although it has Fellner property, it need not be a tile in the sense that I may have infinitely many of such objects because of the huge jump that I do not control. Nevertheless, I can now copy the proof from the Z situation. I am not going into details because my time just finished. Thank you very much. I hope you enjoyed some manipulation with amenable groups, although it was a little remote from the scope of this conference, for which I apologize. Thank you very much.
Tiling system? Do you have any natural tiling system, for example? Toplets, I don't know.
We have a nice
For set two.
Yeah, for Z2, we have a very nice example where actually there are no big jumps. And it is the version of the Hilbert curve. I like this example very much, so thank you for asking. I don't know if I'm able to quickly draw it, but you divide the Z2 into squares. And you order the elements in 4 ways, like so, like, I don't remember actually. Maybe like so, like so. This looks the same. Then you connect like this. I'm very bad at remembering how it works, but you have this kind of pattern. Then you have another one where you have the same pattern maybe here. You have the same pattern only rotated maybe, and then you go up and you cover the whole. No, this is very bad because I ended up here and I have no way to connect. But I have a nice drawing in my paper. I'm sorry, I didn't think to show it. But there is this natural order. And you can shift it, take the closure, you have a multi-order because the big ones are also ordered in the same way. So you have this kind of pattern here on the big ones and then on bigger ones and so on. So you have this Hilbert cube repetitive procedure, except that for the Hilbert cube, you go into smaller and smaller pieces. Here you go outside. And this one has no big jumps, which is very convenient. We don't know. The open question is, for any amenable group, is there a multi-order with no big jumps? That is something we don't know. I will answer a different question. I don't know if there is a general way of saying, I say